Hello, and welcome to the sleepy universe. On a clear night, someone stands by a window and casually raises a hand in front of their face. The moon hangs above the rooftops, bright enough for its outline to appear clearly against the sky. When the person closes one eye and shifts a fingertip slightly to the side, the entire round disk seems to disappear. With only the smallest movement, a world thousands of kilometers wide is completely hidden behind the tip of a finger. The moon, of course, has not become any smaller. It is still out there, still reflecting sunlight, and still holding its true size. The only thing that has changed is the angle each object occupies in the field of view. The finger is very close, while the moon lies nearly 400,000 kilometers from Earth. So for that brief moment, two things of entirely different sizes can appear almost equal. The sky often plays with human perception in this way. An enormous world can fit behind a fingertip, while a structure far larger still can stretch across a broad region of the heavens and go almost completely unnoticed. If the person lowers their hand and looks toward another part of the sky, where the stars of Cygnus are scattered through the darkness, nothing immediately draws the eye. There is no brilliant object like the moon, and no clear outline compelling the observer to stop and look. There are only familiar points of light, with dark spaces between them that seem to contain nothing unusual. And yet, across that ordinary-looking region of sky lies a structure so wide that, if the moon's disk were used as a ruler, 6 moons placed side by side would only just span its width. A structure as wide as 6 moons should be difficult to miss. At least, that is what intuition suggests. Objects that appear larger in our field of view are usually easier to notice. A cloud spread across the horizon stands out more than a faint patch of mist. A building filling half a window is harder to overlook than a distant lamp. So when we hear that a glowing ring covers nearly 3 degrees of sky, it is easy to imagine a giant circle suspended among the stars, broad enough to be obvious even to someone who does not know exactly where to look. But when we look up with the unaided eye, the ring is nowhere to be seen. There are no blue streams of gas curling through the star field, as they do in astronomical images. Orange and red light do not form soft arcs across the sky. The delicate, thread-like structures that sometimes appear so clearly in deep photographs are completely absent from the view of someone standing beneath the night. That region of sky remains quiet and almost empty, as though the 6 imaginary moons placed beside one another were measuring nothing more than a blank space with nothing to see. The difference between the photograph and the real sky can make it seem as though the image has exaggerated the object until it no longer resembles the actual viewing experience. Yet the glowing ring was not added to the darkness, nor was its outline drawn in after the image was complete. Its light is truly reaching Earth. Photons released by that distant gas are still crossing space, entering the atmosphere, and arriving at the human eye, just like the light from the surrounding stars. They simply arrive in numbers that are too small, too scattered, and too close to the brightness of the background sky for the eye to connect them into a complete shape. This is where the paradox becomes especially interesting. An object can be extremely wide without appearing bright. The size it occupies in the sky and its visibility are not two different ways of describing the same thing. One tells us how far the structure extends across our field of view. The other depends on how much light from each small portion of that structure actually reaches the eye, and how strongly that light stands out from the sky behind it. The moon can be covered by a fingertip, yet the light across its apparent surface is strong enough for our eyes to notice it immediately, even when we are not actively searching for it. The much wider ring has no solid surface, reflecting sunlight. It is made of extraordinarily thin gas spread across an enormous volume of space, and the light emitted by that gas is distributed over a very large area of sky. The whole structure may be vast, while each small part remains too faint to form a clear boundary. One way to picture this is with a small amount of color. When that color is placed as a single dot on a sheet of paper, it stands out at once. If the same amount is diluted and spread across a much larger surface, the color does not disappear, but each part of the page holds only the faintest trace. Eventually, the eye can no longer tell where the color begins or ends, even though it is still present across the entire sheet. The glowing ring in the sky is much the same, except that the color here is made of photons that have traveled across thousands of light years. They are not concentrated into a single point, as the light from a distant star is. They are spread along broad arcs of gas, and each small section sends us a signal far weaker than the brilliance suggested by the final photograph. The surrounding sky is not a perfectly black background either. Even far from city lights, the atmosphere produces a faint natural glow. Light from countless distant stars blends into the background. Dust within the solar system reflects a small amount of sunlight, and the human eye adjusts itself to all of these signals at once. A faint object must do more than simply send light toward us. Its light must differ enough from the background for the brain to recognize an edge, a band of gas, or a ring. So perhaps the most important question is not only how wide the structure is. 6 moons placed side by side sounds enormous, but that measurement tells us only how far it stretches across the field of view. Whether we can actually detect it depends on subtler factors. How its light is distributed, how much signal each small region sends toward us, and whether the human eye is sensitive enough to separate those fragile traces from the surrounding sky. So even though it spans such a large area, why do we still barely sense its presence? Perhaps it is not because the ring is too small, and not because it is hidden. Its light still arrives, but it does not gather into a single, clearly defined point. Instead, it spreads outward, soft and thin, across a vast region of the sky, until that very breadth makes it harder to grasp. And to understand how a structure can cover so much of the heavens while nearly dissolving into the darkness, we may need to gently separate two things that intuition often blends together: the sense of size within our field of view and the actual brightness the eye is able to perceive. When the fingertip moves away from the moon, the bright disk immediately returns to its place in the sky, still round, still clear, and seemingly untouched by the comparison that has just taken place. The gesture is so simple that few people would think it touches one of the fundamental principles of astronomy. What our eyes see in the sky does not directly tell us how large an object truly is. It first tells us only how much space that object occupies within our field of view. Human beings live in a world where distance is usually perceived quite naturally. A chair at the far end of a room looks smaller than one placed nearby, yet we still understand that the two chairs are nearly the same size because the room provides many clues that allow the brain to correct what it sees. The floor extends into the distance, straight lines converge, shadows change, and familiar objects appear beside one another. In the sky, most of those clues disappear. A star a few dozen light years away, and another thousands of times farther, can both appear as nothing more than tiny points of light. The moon, the sun, the planets, and enormous clouds of gas all seem to have been placed upon the same flat dome, even though the true distances between them differ beyond easy imagination. For that reason, astronomers do not begin by asking how many kilometers wide an object appears in the sky. They measure the angle it occupies from the observer's point of view. The full circle around us is divided into 360 degrees. From the horizon to the highest point overhead is 1/4 of that circle, or 90 degrees. On this scale, the moon is only about half a degree wide. That may sound small, but in the sky, half a degree is enough to form a disk whose shape the unaided eye can easily recognize, whose changing phases can be followed, and whose surface may even reveal subtle differences in color. If 6 lunar diameters were placed side by side, their combined width would be close to 3 degrees. That is also roughly the span of the entire Cygnus Loop as seen from Earth. This comparison does not mean that 6 real moons could somehow fit inside the gas like 6 marbles inside a box. The moon is simply being used as a familiar ruler in the sky, turning an abstract number into something the eye can understand. 3 degrees may not immediately create a vivid image, but a row of 6 bright moons certainly does. It shows that the remnant is not a tiny point that must be magnified hundreds of times before it can be noticed. In apparent width, it truly covers a substantial region of the sky. That apparent size is shaped by 2 factors that always work together: true size and distance. A large object can look small when it is very far away, while something much smaller can fill most of our view when it is close. A leaf held near the eye can hide an entire building. A relatively small cloud in the atmosphere can sometimes cover a wider portion of the sky than the moon. And the sun, although about 400 times wider than the moon, is also nearly 400 times farther away, causing the 2 objects to appear almost the same size in the sky. It is this remarkable coincidence that allows the moon to cover the sun completely during a total solar eclipse. With the Cygnus Loop, the story unfolds on an entirely different scale. This structure lies thousands of light years from Earth and has a true diameter of more than 100 light years, depending on the distance value used in a particular measurement. Light itself would need more than a century to travel from one side to the other. If a signal were released from one edge of the shell, several generations of human beings could be born and grow old before it crossed the full width to the opposite side. A structure that vast, even from such a great distance, is still large enough to span nearly 3 degrees in our field of view. Yet we should also be careful with the image suggested by the word loop. The Cygnus Loop is not a perfect circle drawn evenly across the sky, nor does it have a sharp boundary that can be measured cleanly from one end to the other. It is made of many glowing arcs, separated bands of gas, and regions of emission with different levels of brightness, all belonging to a vast shell left behind by the explosion of a star. Some parts of the shell are much more visible, while others are so faint that they almost dissolve into the background sky. When we say that the entire remnant is as wide as 6 moons, we are measuring the overall region occupied by these fragments, not describing a uniformly bright ring on every side. This also explains why even someone who knows exactly where to look would still struggle to define its boundaries with the naked eye. With the moon, the beginning and end of the disk are easy to identify. The light changes quickly from its bright surface to the darker sky beside it, creating an edge the brain recognizes immediately. With a diffuse cloud of gas, brightness changes gradually. There is no place where the sky suddenly announces that the remnant begins here and ends there. The faint arcs slowly fade, break apart, and then reappear elsewhere. So the full width of the structure becomes clear only after many separate regions have been recorded and placed together on the same map. The method of measuring objects like this existed long before modern astronomical cameras. Skywatchers once used stars as reference points, recording the position of a faint band of light relative to nearby stars and estimating the angular distance between them. The sky became an enormous coordinate system in which distances were measured not in meters, but in degrees, arc minutes, and arc seconds. 1 degree is divided into 60 arc minutes, and each arc minute is divided into 60 arc seconds. The moon is about 30 arc minutes wide, while small details in telescope images may span only a few arc seconds. With this system, even a dim and irregular patch of light on an everyday scale, the hand can also serve as a rough measuring tool. When the arm is fully extended width of the little finger usually covers about 1 degree, though the exact value varies slightly from person to person. 3 fingers held together can cover a region of sky close to the full width of the Cygnus Loop. A closed fist usually spans about 10 degrees, while the distance from the little finger to the thumb on an outstretched hand can approach 20 degrees. These simple estimates cannot replace scientific instruments, but they remind us that apparent size is not a distant or unfamiliar concept. Every time we raise a hand toward the sky, we are unknowingly placing an angular ruler in front of our eyes. If someone found the correct region within Cygnus and placed 3 fingers over it, the patch of darkness hidden behind the hand could contain nearly the entire extent of the remnant. Within that small area, which seems as though it should be easy to observe, lie arcs of gas that have expanded through space for thousands of years, layers of matter colliding with the material between the stars, and atoms still releasing light after an event that occurred before most of recorded human history. Its apparent width reveals that the object is not small in the sky at all. It is simply present in a way very different from what intuition expects. This difference becomes clearer when the Cygnus Loop is compared with more familiar objects. Many distant galaxies appear extremely small because of their immense distances, even though their true diameters may reach hundreds of thousands of light years. Jupiter is more than 10 times wider than Earth, yet to the unaided eye it looks like little more than a point of light. By contrast, an auroral band or a thin cloud in the atmosphere can stretch across much of the sky because it is so much closer. True size, distance, and viewing angle are constantly working together, creating a sky whose appearance rarely tells the full physical story behind it. So the phrase, "as wide as 6 moons," answers only one very specific question: how much of the observer's field of view the structure occupies from Earth. It does not tell us how strongly the gas is glowing, nor whether the human eye is sensitive enough to detect it. A large billboard in a completely dark room can be harder to see than a small lamp that is switched on. In the same way, an object can span 3 degrees of sky without producing enough contrast to form a clearly recognizable shape. This is where our intuition about size begins to fail. We often use the word large as though it also means conspicuous, but the sky does not follow such a simple relationship. Width tells us only how broadly the light is distributed. If the amount of light coming from each part of that region is too low, spreading across a larger area does not make the object easier to see. Sometimes it makes the signal appear even more diluted within our field of view. The moon remains the perfect ruler for imagining the width of the remnant because it is familiar, sharply defined, and bright enough that the eye never has to search for it. Yet it is the difference between the two objects that leads us deeper into the story. One is a rocky world with a surface that reflects sunlight and a crisp edge against the sky. The other is a thin shell of gas spread across a region many times wider, with no solid surface and no concentration of light forming a bright disk. 6 moons tell us how wide the remnant is. They cannot yet explain why that region of sky still appears almost empty to the human eye. To move closer to the answer, we must leave apparent size behind and look at how the light is divided across the entire structure. Because sometimes an object does not disappear because it is too small, but because its light has been spread so thinly that each individual part remains only the faintest trace against the sky. When an object is too faint to stand out, what matters is not only how much light it sends toward us, but also how much light surrounds it. A candle may appear clearly in a dark room and then nearly disappear when carried outside at noon, even though the flame itself has not changed. The signal is still there, only the background has become stronger. In the sky, the Cygnus Loop faces a similar background, far dimmer than daylight, but never entirely absent. From the ground, we often describe the space between the stars as darkness. That description matches what our eyes seem to experience. After sunset, the blue of day slowly fades, rooftops become dark silhouettes, and the sky appears to open into a deep black expanse. Yet if a sufficiently sensitive instrument were pointed upward, it would not record a completely empty background. Even on a moonless night, far from streets and populated areas, a thin layer of light still covers the entire sky, created by many different sources overlapping one another. Part of that glow originates within Earth's own atmosphere. Far above the familiar clouds, atoms and molecules can absorb energy during the day and release faint light at night. This phenomenon is commonly known as airglow. It is too dim for the eye to recognize as a distinct layer of light. But in long exposure photographs, it can sometimes appear as bands of green, pale red, or broad ripples of illumination. The sky may seem motionless, while the upper atmosphere continues to glow quietly through processes unfolding beyond human awareness. Air glow is nowhere near strong enough to turn night into day. Yet for a remnant with extremely low surface brightness, even a small amount of background light becomes significant. Imagine a white chalk line drawn very lightly on a blackboard. When the board is clean, the line may be visible. If the entire surface is covered with a layer of gray dust, the mark is still there, but it no longer stands apart as clearly as before. The light from the Cygnus Loop is like that faint chalk line, while the atmosphere places it against a background that is never completely dark. Beyond Earth's atmosphere, the solar system adds more light of its own. The space between the planets is not truly empty. It contains tiny particles of dust, most of them too widely scattered to form a clearly visible cloud. When sunlight strikes this dust, some of it is scattered back toward Earth, creating the gentle glow known as zodiacal light. From a very dark location, during the right season and at the right time, it may appear as a faint cone rising from the horizon along the sun's apparent path through the constellations. Zodiacal light is often described as a subtle sight for attentive sky watchers, but for diffuse objects, it is also part of the background they must overcome. The Cygnus Loop does not always lie directly within the brightest region of the zodiacal glow, but the principle remains the same. The sky contains light from many layers of space, and all of it enters the eye or the sensor before we can separate the particular signal we want to see. Farther still is the light of the Milky Way. On nights dark enough, a broad luminous band can appear across the sky, not because a single object is glowing there, but because countless stars are too distant and too densely packed for the eye to distinguish one from another. Their light blends together, along with dark clouds of dust and interstellar gas, creating a background with a complex structure. The Cygnus Loop lies in a star-rich region of the sky, so its faint arcs do not appear against a simple black emptiness. Behind them are dense star fields, regions of dust, and many other weak sources of light scattered along our line of sight through the galaxy. This makes detecting a diffuse structure very different from finding a star. A point of light can stand out simply by being brighter than the small area immediately around it. With a shell of gas nearly 3 degrees wide, the brain must detect a very slight change extending across a large region, while thousands of stars within and around that area create much stronger points of contrast. The eye is naturally drawn to distinct points of light, while the thin glow between them can easily be dismissed as an insignificant part of the background sky. There are also nights when the sky appears clear, even though water vapor remains in the air. Humidity does not always form clouds, but tiny droplets of water and particles of dust can scatter light from the ground, from the moon, or from distant communities. A city beyond the horizon may not be directly visible, yet its glow can still rise into the sky as a pale dome. The weak signal from the remnant must pass through this air before reaching the observer, and every layer of scattering makes the background brighter, or softens features that were already difficult to distinguish. In urban environments, this effect becomes much more obvious. Streetlights, signs, windows, and industrial areas send light upward into the atmosphere. Some of that light escapes into space, but some is scattered back toward the ground by air molecules and small particles. As a result, the sky above a city may appear gray, pale yellow, or milky white, depending on the type of lighting and the atmospheric conditions. The brightest stars remain visible, while fainter stars disappear one by one. Objects with low surface brightness often vanish before the observer fully realizes how much the sky itself has changed. The Cygnus Loop is not literally blocked by city light in the sense that a curtain of matter has been placed in front of it. Photons from the distant gas still cross space and continue toward the ground. They are simply mixed with a much larger number of photons arriving from nearly the same directions. A sensor records all the light entering it, and the human eye has no label telling it which photons came from a supernova remnant and which came from a light bulb a few kilometers away. To separate the signal, an observer must rely on contrast, wavelength, and the amount of time spent collecting light. This can be understood through a very quiet sound. In a silent room, the ticking of a clock in a distant corner may be easy to hear. When a fan begins to run, the ticking does not disappear, but it sinks into the steady sound around it. If traffic noise rises outside as well, the ear may become almost unable to separate the clock's rhythm from the background. Something similar happens in the sky, except that the signal arrives not as sound, but as light. The shell of gas is still speaking, but the sky around it is never completely silent. The important idea here is contrast. The eye does not respond only to absolute brightness. It is highly sensitive to differences between neighboring regions. A sharp boundary is easy to detect because the light changes quickly from one level to another. But when brightness shifts gradually across a wide area, the brain may treat the entire variation as part of the background. The brightest arcs of the Cygnus Loop have somewhat clearer edges and are therefore easier to observe, while the fainter shell between those arcs nearly dissolves into the sky. The edge of the moon offers an almost perfect contrast. Its bright disk ends abruptly at the rim, where the sunlight reflected from its surface gives way to the dark sky behind it. The brain can identify its round shape immediately. The Cygnus Loop has no solid surface like this. Its light gradually increases along certain bands of gas, fades in the neighboring regions, and then appears again somewhere else. Its span of nearly 3 degrees is formed by many broken structures, so even when one section approaches the threshold of visibility, the eye still struggles to assemble them all into a single ring. The moon also directly affects the observation. When it is present in the sky, sunlight reflected from its rocky surface enters the atmosphere and spreads outward, brightening the background far beyond the lunar disk itself. A full moon night may be beautiful for viewing the landscape, but it is poorly suited to searching for faint nebulae. The Cygnus Loop remains in the same place and does not change significantly in brightness over a few nights, yet the contrast between it and the surrounding sky becomes lower, making its already delicate bands of gas even harder to detect. When the moon has set, the sky is clear, and the observer moves far from artificial lights. Conditions improve. The background becomes darker, more faint stars emerge, and the regions of the Milky Way begin to reveal greater structure. Yet even under these nearly ideal conditions, the entire remnant does not unfold like a long exposure photograph. Some of its brighter sections may be detected through a wide-field telescope or suitable binoculars, especially when a filter is used to reduce unwanted light. They usually appear as extremely faint, soft, colorless streaks, requiring the observer to spend time at the eyepiece before becoming certain that they have truly seen them. The moment a faint band of light is recognized rarely feels like discovering a new star suddenly appearing in the eyepiece. At first, the region of sky only seems slightly different. When the eye shifts, the glow may disappear. When the observer looks slightly to the side, it returns like the thinnest ripple. The view must be compared again and again, with small changes in where the eye is directed, while the sky drifts slowly across the field of view. The structure does not step out of the darkness all at once. Instead, it is gradually confirmed through subtle differences that repeatedly appear in the same place. This reveals that a dark sky is not a simple condition that is either present or absent. There are many degrees of darkness, shaped by artificial light, the moon, humidity, dust, altitude, the observing season, and even the position of the target relative to the horizon. When an object is bright, these differences may not matter very much. When the signal rises only slightly above the background, every one of those factors can determine whether it appears or disappears. For that reason, when someone looks up and fails to see the Cygnus Loop, it does not mean its light has not reached Earth. It means only that, under those conditions, the difference between the remnant and the background sky is not strong enough for the visual system to separate them. The structure still stretches across a region as wide as 6 moons, and the atoms within its gas still emit their characteristic wavelengths, but the signal blends into a background of atmosphere, dust, stars, and artificial light before it becomes an image in the mind. A darker location may bring the brightest arcs closer to the threshold of visibility, but reducing the light outside the observer solves only part of the problem. The rest lies within the eyes looking upward. As the light fades, the visual system changes the way it works, favoring sensitivity over color and adjusting slowly over the course of several minutes. It can detect remarkably weak signals, but it cannot wait and accumulate photons in the way an astronomical sensor can. The glowing ring must do more than rise above the background sky. It must also pass through the limits of a sense shape to observe the nearby world around us. And once the night has been made as dark as possible, those limits determine which parts of the remnant remain within sight and which continue to dissolve into the darkness. When a wide-field image of the Cygnus Loop appears on the screen, the first shape the eye often notices is a broad curve wrapped around a darker region in the middle. Bright arcs lie along both sides, some of them connected in fairly clear fragments, while others fade away and disappear into the starfield. This arrangement makes the name loop feel natural, as if somewhere in space an enormous ring of gas were lying almost flat, facing Earth. But that is only the image projected onto the sky. The real structure is not like a thin ring placed among the stars. It is closer to a vast shell expanding in every direction, a three-dimensional surface surrounding the region of space where the original star once existed. That shape is not perfect, nor is it smooth like a sphere made in a laboratory. Interstellar material is not evenly distributed. The shock wave does not encounter the same environment in every direction, and over thousands of years, the shell has become wrinkled, distorted, and broken into pieces. Even so, the idea of a giant bubble still helps explain why the brightest regions often appear around the edges. Imagine a transparent sphere made from an extremely thin layer of material. When you look straight through the middle, the light passes through the shell at the front and then through the shell at the back, each time across a relatively short distance. But when you look near the edge, the line of sight no longer cuts through the shell almost at a right angle. Instead, it runs along the shell for a much longer stretch. More glowing material lies along the same line of sight, so the light from those regions adds together, making the rim stand out. In astronomy, this effect is often called limb brightening. It does not necessarily mean the shell contains more material at the true edge of the object. The rim appears brighter mainly because of the way we are looking through a three-dimensional structure. The line of sight passes through a greater length of gas, allowing more glowing atoms to contribute to the same small patch of sky. Near the center, where the path through the shell is shorter, the signal can be weaker and more easily lost in the background. A soap bubble under gentle light suggests something similar. The face of the bubble can look almost transparent, while its outline is often easier to see because light is reflected and refracted through the thin film at a different angle. The Cygnus Loop is not a soap bubble, and its light is produced by excited gas rather than simply reflected from the outside. But the image is still useful. A thin surface can appear as a bright ring not because the inside is absolutely empty, but because the edge allows light to accumulate more clearly within our view. That shell began to form when a massive star reached the end of its life and exploded as a supernova. The original explosion released an enormous amount of energy, driving material from the star outward at very high speed. The intense flash of that event has long since faded, but the ejected material and the shock wave it created continue to move through the interstellar medium. Over time, that wave has swept up gas and dust already present in space, compressing them, heating them, and making them glow. What we see today, then, is not simply leftover pieces of the original star drifting freely through space. An important part of the glowing structure is interstellar material that has been affected by the shock wave. Much like a wave on the surface of water is not a separate block of water racing across a lake. A shock wave carries energy through a medium and changes the state of the gas at each location as it passes. Material ahead of the wave is compressed, its temperature rises, atoms lose electrons or become excited, and then they emit light as they return to lower energy states. In the early stages, the material from the explosion moved extremely fast and may have expanded almost freely. Gradually, it swept up more and more surrounding gas, changing the nature of its motion. The energy continued to spread outward, but the shell became more strongly shaped by the environment it encountered. Regions where the interstellar gas is thinner allow the shock wave to travel farther. Denser regions slow it down, compress it more strongly, and sometimes make it shine more clearly. It is this unevenness that causes the Cygnus Loop to lose the simple symmetry of a perfect sphere. If the space around the star before the explosion had been completely uniform, the shell might have expanded into a shape that was closer to round and evenly balanced. But the interstellar medium is more like an extremely diffuse landscape, with regions of different density, clouds of gas, empty cavities, and traces left behind by earlier generations of stars. The shock wave has to move through that landscape, so its boundary is stretched outward on one side, slowed on another, and rippled across many different scales. In images, this complexity can be hidden by the overall impression of a circle. The human brain is very good at connecting separate curves into a familiar shape. When we see one bright arc in the east, another curved region in the west, and a few faint bands in between, we naturally imagine the complete circle to which they all belong. Astronomers also use that broad outline to describe the entire remnant, but they do not assume that every part of the shell must be equally bright or lie on a single flat plane. In reality, each bright arc may sit at a different depth relative to Earth. A filament that seems to run across the sky may belong to the front surface of the shell. Another may lie near the rim or on the far side. A two-dimensional image stacks these layers of space on top of one another, making regions separated by many light years in depth appear to sit side by side on the same plane. Astronomy often has to work with this kind of depth compression because we observe the universe from a single position and receive light along individual lines of sight. To infer the three-dimensional structure, researchers do not rely only on the shapes seen in images. They examine the motion of the gas, the shifting of spectral lines, temperature, density, and the way different emission regions are distributed. If one part of the shell is moving toward Earth, its light may shift slightly toward shorter wavelengths. If it is moving away, the wavelengths may be stretched longer. These subtle changes make it possible to distinguish some regions that lie in front, behind, or moving almost sideways across our view. A map like this does not produce a perfect image of the entire bubble, but it helps confirm that the ring seen on the sky is the projection of a deeper structure. The bright arcs are not simply arranged in a flat circle. They belong to a shell moving through three-dimensional space, with many parts tilted at different angles relative to the observer. That geometry also explains something that may seem contradictory. If the gas shell surrounds such a large region, why does the middle of the loop not glow fully like a cloud? Because the light is not distributed evenly throughout the entire volume. Most of the strongly glowing gas is concentrated in a relatively thin layer where the shock wave is acting now or has only recently passed through. The inside of the shell may contain hot gas and diffuse material, but in visible light, it does not necessarily glow in the same way or with the same intensity. When we look through the center, we mainly see the shell at the front and the shell at the back. When we look near the rim, our line of sight remains within the glowing region for longer, causing the signal to increase. Even so, the rim does not form a continuous circle. Low-density regions may emit light that is too faint, while areas interacting with denser clouds of gas become more prominent. Where the shock wave moves through a thin medium, the temperature and ionization state may differ from places where it strikes a gas cloud. Different elements glow strongly under different conditions, so a filter sensitive to oxygen may reveal a structure that does not look exactly like one focused on hydrogen. For that reason, a color image of the Cygnus Loop does more than highlight an outer boundary. It separates different physical layers within the same shock wave. Blue regions may emphasize light from ionized oxygen, while reds and oranges often bring out other emissions, depending on how the data were collected and assigned color. The colors do not turn the shell into a solid surface. Instead, they show that within the bright bands, many states of gas can exist side by side. If we could leave Earth and view the remnant from another direction, its observed shape would also change. Arcs that now lie along the rim from our current perspective might shift inward in the projection, while faint regions at the front or back could become the new outline. The loop is not an absolute property of the object from every direction. It is the result of a three-dimensional structure meeting the particular line of sight we have from our position in the Milky Way. The same idea appears in many other astronomical objects. A shell of gas around a star can appear as a circle. A tilted disk of dust can become a straight line, and a stream of material winding through space can project into a shape that seems to cross itself, even though its true parts never touch. The sky is a two-dimensional observing surface, carrying the traces of a three-dimensional universe, and every shape has to be read with a certain care. For the Cygnus Loop, this way of reading makes the paradox of visibility easier to understand. The entire structure spans the width of 6 full moons, yet its visible light does not fill that area evenly. It is concentrated in thin layers, rim segments, and places where the shock wave meets conditions favorable for the gas to glow. Much of the structure remains faint, so the eye does not receive a complete ring, but only, under good conditions, catches a few separate arcs. An observer at a telescope may follow one glowing band for several minutes, only to see it fade into the star field. When the field of view shifts elsewhere, a new segment may appear with a slightly different curve, but the gap between the two parts makes their connection unclear. Only when the regions are photographed, aligned, and placed beside one another does the overall shape of the shell emerge. The sense of a loop, then, does not come from a single bright line that the eye can take in all at once, but from recognizing and assembling many parts of the same structure. Still, looking through the shell only explains why the rim is brighter than the center. It does not fully explain the thread-like appearance of the most prominent bands of gas. If the shell were only a smooth, uniform sphere, its edge might appear as a relatively continuous bright band. In real images, the arcs break into many thin lines, bending, running close together, and then separating again, more like folds of fabric than the edge of a simple sphere. The origin of that shape lies in the uneven surface of the shell itself. The shock wave is bent, folded, and wrinkled as it moves through an environment with changing density. A broad sheet of gas, if viewed edge-on, can look like a thin filament. Several folds in the same sheet can appear as parallel lines, even though they are actually connected in space. So the loop on the sky is not only the projection of a bubble. It is also a collection of rippled sheets of gas, and each bright band reveals a place where our line of sight runs along a fold long enough for the light to add up. To understand why those filaments are both delicate and complex, we need to move closer to the surface of the shell, where a broad sheet of gas can become a narrow line of light simply by being viewed from the right angle. In some places along the Cygnus Loop, the light does not spread out into broad patches, but gathers into extremely thin, like a soft, elongated curve. It's like strands of silk laid across the sky. They may run parallel for a while, split into several branches, and then gradually fade among the stars, leaving the impression that narrow streams of gas are drifting separately through space. But the shape that appears in the image is only the final result of observation, where every depth within the object has been compressed onto the same two-dimensional surface of the sky. A bright band that looks like a thread does not necessarily have the true shape of a thread. It may be the edge of a much broader sheet of gas, turned almost edge, on toward Earth. Think of a very thin piece of fabric hanging in a softly lit room. When you look directly at the flat part of the fabric, the light passes through only a relatively short layer of material, so the surface may appear faint. Where the fabric folds, the line of sight passes through more layers, making the fold darker and easier to see. If the entire sheet is slightly wrinkled, the parts turned edge-on toward the observer will appear as narrow lines, while the regions connecting them still exist, but nearly disappear into the background. The Cygnus Loop creates a similar effect, except that the fabric here is a layer of gas stretched across distances measured in light years, and the folds are formed as a shock wave travels through the interstellar medium. The shell of the remnant is not expanding into a completely uniform void. Although the interstellar medium is incredibly thin compared with the air around us, it still contains atoms, dust, magnetic fields, and regions of varying density. In some places, the gas is so sparse that the shock wave can move faster. In others, denser material slows the wavefront down and compresses the gas ahead of it more strongly. When different parts of the same wavefront no longer move at the same speed, the surface gradually bends, stretches out of shape, and forms complex ripples. This distortion happens on many scales. A dense cloud of gas may slow an entire large region of the shell, while smaller changes in density create delicate wrinkles within it. Over thousands of years, small differences are stretched and amplified, until the wavefront no longer resembles a smooth sphere, but becomes a broad, wavy, uneven surface. When one part of that surface tilts at just the right angle, the line of sight from Earth runs along the gas layer for a longer distance, allowing light from many regions lying behind one another to add together at the same position in the sky. It is this accumulation that makes a broad surface appear as a narrow bright band. This also helps explain why some bright lines run nearly parallel to one another. They are not necessarily several independent streams of gas moving in the same direction, but may be different folds within the same large sheet of gas. A rippled surface, when viewed from an angle, can reveal multiple edges at different positions. In an image, those edges appear as separate bands, even though in three-dimensional space, they remain connected through regions too faint to see clearly. The dark gaps between the bands, then, are not always true empty spaces. The gas layer may still continue through them, but its angle has changed, so the line of sight passes through only a shorter thickness. When the number of glowing atoms along the same direction decreases, the signal also weakens and more easily blends into the sky background. A small change in geometry can make a bright band gradually disappear, then reappear where the surface once again turns edge-on toward the observer. If we could leave Earth and view the remnant from another direction, many familiar bright lines would no longer keep the same shape. A band that is now prominent along the rim might shift inward in the projection, while a region that appears very faint from our position could become a clearer boundary. This shows that the glowing filaments are not fixed strokes drawn onto the shell, but the result of a three-dimensional structure meeting the right viewing angle. They tell us as much about the geometry of our line of sight as they do about the glowing material itself. Still, viewing angle is only part of the story. For a fold of gas to become clearly visible, it also needs the right physical conditions to emit light. The shock wave compresses and heats the gas, while also stripping electrons from some atoms. As the material behind the wavefront gradually changes state, electrons can recombine or move between different energy levels, releasing light at characteristic wavelengths. Hydrogen, oxygen, and sulfur do not glow in the same way under all conditions, so different layers of the same region of gas can stand out in different colors when observed through the appropriate filters. A blue band lying near a red or orange region, therefore, does more than create a beautiful contrast in the image. It may reveal gas in different states of ionization, located at different positions behind the shock wave, or given different amounts of time to cool. The colors in astronomical images are often processed to clarify specific wavelengths, but the information behind them still comes from real light emitted by atoms. By looking at how those colors are arranged along a narrow filament, astronomers can study how matter changes after the shock wave passes through. If we could move close to one of those bright lines, the scene would probably not resemble a glowing wall of gas. The material would still be extremely diffuse, so thin that a vast volume would contain only a very small number of particles compared with the air on Earth. Its clear brightness appears only when we look through a long enough path where the faint light from countless atoms is added together. A single region may glow very softly, but when trillions of tiny segments lie along the same line of sight, the total signal becomes strong enough for a sensor to record. You might compare this to a very thin layer of mist. When you are standing inside it, the mist is present all around you, but it does not form a clear wall. Seen from a distance across a longer path, many water droplets overlap within your view, and the mist becomes a visible, glowing band. The Cygnus Loop shows the same influence of line of sight length, even though the environment and the mechanism of emission are completely different. Each narrow band is a place where geometry helps place a large amount of weak emission onto the same small region of the sky. The surface of the shell continues to change as the shock wave moves outward. Places that encounter a thinner medium can expand more quickly, while regions interacting with dense gas clouds slow down and become more complex. Along a bright arc, the shape of the gas folds may preserve a record of that change. A relatively smooth segment suggests a more uniform environment, while an area that splits into many lines or bends sharply may reflect the complicated structure of the gas the wavefront has just encountered. In that sense, the bright bands are not only traces of the dead star, they also preserve an image of the space through which the explosion is moving. The interstellar medium is normally very difficult to see directly, but when a shock wave sweeps through it, the material is compressed and begins to glow, revealing dense regions, thin regions, and clouds of gas that once existed almost invisibly. The remnant becomes an indirect way of observing the structure of the space around it, much like a breeze reveals the shape of a curtain by making its surface tremble. Astronomers cannot fly outside the Cygnus Loop and view the shell from every direction, so its three-dimensional structure has to be inferred from many kinds of evidence. Images show the positions, curvature, and thinness of the bands. Spectra reveal whether the gas is moving toward Earth or away from it along our line of sight. Photographs taken years apart show the extremely small motion of the wavefront against the background stars, while observations at different wavelengths reveal parts of the shell that do not stand out in visible light. Each measurement provides only one slice of the picture, but when they are placed together, the model of rippled sheets of gas becomes more convincing than the image of countless separate strands. A thin bright line may be where the gas layer turns edge-on toward us. Two parallel lines may be two folds in the same surface. A segment that suddenly disappears may simply mark a change in viewing angle. What appears disconnected in an image may sometimes remain continuous in real space. This way of understanding also makes it clearer why a structure as wide as 6 full moons does not appear as a complete ring. Most of the shell does not have enough surface brightness to rise above the background, or it is not positioned at a favorable angle for its light to accumulate. Only along certain rims and folds, where the line of sight path is longer and the gas glows strongly enough, do the thin arcs emerge from the sky. The regions connecting them may still exist, but they fall below what the unaided eye, or a brief observation, can recognize. By this point, the dark areas between the bright bands no longer feel entirely empty. They may contain other parts of the same shell, turned at an angle that spreads the light too broadly, or emits more strongly at wavelengths the eye cannot see. The remnant does not vanish where the outline breaks. Only the way it appears changes, depending on density, temperature, the state of the gas, and the geometry of the line of sight. The first half of the story, then, gradually closes around one unified idea. Its apparent size shows that the Cygnus Loop spans a very large region of sky, but its light is not distributed evenly. Its low surface brightness causes much of the structure to blend into the background. The sky has never been absolutely dark, and the human eye can recognize only certain bright arcs under favorable conditions. The shell itself is also rippled and three-dimensional, so what stands out most clearly are the edges and folds of gas viewed from the right angle. From here, our perspective shifts toward a different approach. If the eye catches only a few faint segments and cannot hold enough light to connect them, how can humans reconstruct the entire remnant loop? The answer begins with an instrument capable of gathering light through an area wider than the pupil. But its role is not simply to make everything larger. A telescope first opens a wider entrance for photons that have already traveled for thousands of years, then hands them to a system that can record them for longer, separate them by wavelength, and assemble the scattered pieces into a unified image. The light left the Cygnus Loop long before any human knew that a giant shell was expanding in that region of the sky. Individual photons radiated outward from the hot gas, crossed the space between the stars, traveled thousands of light years, and arrived at Earth from very specific directions. Most of them never encounter an observing instrument. Some strike the atmosphere, some reach the ground, and a very small fraction happen to fall into the open aperture of a telescope pointed toward the constellation Cygnus. In that instant, the true role of the telescope begins. It does not call more light from the remnant, nor does it make the gas filaments shine more strongly out in space. All it does is collect more photons than the unaided eye, then arrange them according to their direction so they can form an image that can be observed or recorded. In darkness, the pupil of the eye can widen to gather more light, but its diameter still measures only a few millimeters. The mirror or lens of an amateur telescope may be tens of centimeters wide, giving it a much larger light-collecting area. The difference is not simply in diameter, because light-gathering power increases with the area of the opening. A mirror only a few times wider can receive far more photons from the same region of the sky. You might think of a very light rain. If you place a small cup outside, the amount of water collected after a few minutes is almost negligible. If you replace it with a wide basin, the rain has not become any heavier, but more drops fall into the container. A telescope does the same thing with light. It does not change the distant source, but simply widens the area that can receive the photons already arriving. With stars, this benefit is often easy to notice. The light from a distant star is concentrated into a very small point in the image, so when a telescope gathers more photons, that point of light can stand out more clearly against the sky. The Cygnus Loop presents a different problem. Its light does not come from a point, but is spread across broad arcs of gas, with each part of the structure sending photons from a slightly different direction. A telescope can collect more light from each region, but it must also preserve the way that light is distributed across the image. This is why a diffuse object does not simply become brilliant just because it is viewed through a large telescope. When the image of a gas arc is magnified, it covers a larger area on the retina. The light collected from that region is also spread over a wider visual area, so the brightness of each small part does not increase in the intuitive way one might expect. The shape may become clearer, and the curve may be easier to follow, but the surface of the gas band still remains soft and faint. Magnification, then, is not a ladder that moves in only one direction, where every step higher helps reveal more. If the magnification is too low, a thin band of gas may be so small that the brain struggles to separate it from the star field. Increasing it just enough can enlarge the structure, helping the observer recognize its curve, width, and variations in brightness. But if the magnification continues too far, the light is spread out even more. The field of view narrows, and the gas band can become so dim that it loses the contrast it had just gained. Observing a faint nebula is therefore like adjusting your distance while reading a very pale line of text. From too far away, the small strokes blur together. At the right distance, the letters begin to take shape. But if they are enlarged too much while the contrast remains unchanged, all you see are broad, soft gray regions, and the whole word becomes difficult to recognize. A good telescope is not merely one that makes the image larger. It is an optical system that helps find the right balance between size, brightness, and field of view. The Cygnus Loop makes that balance especially important because the entire remnant spans nearly 3 degrees across the sky. Many telescopes, when used with ordinary eyepieces, show only a small part of the structure at a time. The observer does not see the whole loop contained in the frame like the moon. They begin with one prominent arc, move the telescope along the curve, pause at stars that serve as landmarks, and then continue into the neighboring region. That experience is closer to walking along a coastline than looking down at an island from above. At each point, only one stretch of the shore appears before the eyes. In some places the curve is clear, in others it sinks behind haze, and the connection between segments has to be held in memory as the observer shifts the field of view. The scale of 6 full moons is not just a striking phrase for a title. It truly determines how the object is observed. A wide-field optical system can keep more of the remnant within the same frame, giving a clearer sense of its overall scale. In return, the smaller folds of gas inside each arc are not enlarged as much. A telescope with a longer focal length or higher magnification allows a closer look at the delicate bands, but at that point, the complete loop disappears from view, leaving only a small region of the shell. Each choice answers a different question: how wide the structure is, or what details lie inside one bright arc. Even with the right choice, the view through the eyepiece remains far more subtle than an astronomical photograph. A gas band that stands out clearly in an image may appear only as a slight change in the background sky. Color is almost absent because the number of photons arriving at each moment is not enough to strongly stimulate the cone cells of the eye. The brightest portion may become a thin gray streak, the next segment fading away into darkness, forcing the observer to use averted vision and hold the eye steady long enough to confirm that the structure is not just a passing impression. On a good night, the moment of recognizing the band can arrive very gently. At first, the star field looks ordinary, and then one region begins to seem a little less dark than its surroundings. When the eye shifts slightly to the side, the curve becomes a bit clearer. When looking straight at it, the signal weakens again. After this is repeated a few times, the arc of gas gradually takes shape, not because it has become brighter, but because the observer has learned to separate a very small difference from the background sky. A larger aperture helps bring more photons into the eye, but it also collects light from everything lying in the same direction: the atmosphere, scattered light, stars, and other background sources. If the signal from the remnant increases along with the brightness of the sky, the contrast does not necessarily improve very much. For that reason, a large telescope under a light-polluted sky does not automatically outperform a smaller telescope in a truly dark location when the target is a diffuse structure. The essential point is still the difference between the gas band and the background around it. Some observing filters can help by allowing important emission wavelengths from the nebula to pass through while reducing many other components of light. For the Cygnus Loop, emission from ionized oxygen is often very prominent, so an appropriate filter can make arcs that were once vague become easier to recognize. The object does not emit more light. The background is simply reduced in relative terms, like a quieter room that allows a faint melody to be heard more clearly. The change through a filter is sometimes subtle, but meaningful. A region that previously felt only slightly bright may begin to take the shape of a curve, while a band that had already been noticed may hold its form longer as the eye moves. Even so, a filter does not turn the eyepiece into a color screen, and it cannot rescue every part of the remnant from the darkness. Regions with signals that are too weak still remain beyond direct visibility, and the full loop still has to be traced piece by piece. By this point, the telescope has greatly expanded the limits of the unaided eye. It collects more light, forms an image at a useful scale, and allows the observer to choose a field of view suited to the size of the object. The brightest arcs can be recognized, the larger folds of gas gradually take shape, and part of the structure begins to separate itself from the sky background. And yet, the telescope still delivers light to a visual system that operates only in the present moment. Photons arriving in the first minute are not stored by the eyes, so they can be added to photons arriving in the 10th. An observer may continue looking for a long time, but each moment is still a new act of reception, not a continuous exposure. It is at this limit that visual observation and photography begin to separate into two different paths. A sensor placed at the focus of the telescope does not need to turn photons into an immediate impression. It can preserve the signal over many seconds or many minutes. Light that arrives early and light that arrives later contribute to the same frame, allowing a gas band too faint in any single instant to gradually form a measurable trace. As many such exposures continue to be combined, regions that once sank into the background begin to appear. A telescope, then, is not the complete answer to the invisible loop. It is the first doorway, wider than the pupil and precise enough to guide the light back to the correct position. Beyond that doorway, there still needs to be a place that can wait, preserve, and accumulate photons that arrive too sparsely for the human eye to connect them into a shape. This is the most important shift in the way humans see the Cygnus Loop. When light no longer has to prove its presence in a single instant, time becomes part of the observing instrument. And precisely because a sensor can wait longer than the eyes, faint lines of gas are given a chance to emerge from the darkness, little by little, until the scattered pieces begin to move closer to the shape of the complete loop. When the light from the Cygnus Loop passes through the optical system and comes to focus inside a telescope, it has completed almost its entire journey of thousands of years. If an eyepiece is behind the telescope, those photons continue into the eye and exist only as part of the visual impression of the present moment. A faint band of gas may appear, fade, and return as the observer shifts their gaze. But if the eyepiece is replaced with a sensor, that same amount of light enters a very different process, where each photon no longer passes away immediately after being received, but can be preserved, measured, and accumulated over time. The surface of the sensor is divided into millions of pixels, each responsible for a very small part of the sky. When a photon strikes the light-sensitive material, its energy creates a tiny electrical signal. A single impact like that means very little on its own, but light from the same region of gas continues to arrive, slowly and sparsely, and each small contribution is stored throughout the exposure. By the time the recording ends, the value in each pixel no longer represents one isolated instant, but reflects the total amount of light that has fallen there over the previous seconds or minutes. The difference between looking for a long time and exposing for a long time lies precisely in this ability to store the signal. A person can stand at the telescope for a long while, keep their gaze on the same region of sky, and patiently search for a faint arc of gas, but the visual system still keeps refreshing the image. The signal received in the first minute is not preserved, so it can be directly added to photons arriving in the 10th. A sensor, however, allows light to accumulate into a single measurement, letting a region that is too faint in any individual moment gradually leave behind a more stable trace. For an object with low surface brightness like the Cygnus Loop, time becomes inseparable from the image. The brightest segments of the shell may appear fairly quickly, while the weaker connecting regions need more time to rise above the background. The sensor does not require the entire structure to appear at once. It only needs photons to keep arriving from the same position, allowing the signal to grow until the difference between the gas band and the surrounding sky becomes large enough to measure. However, the sky does not remain still on the sensor simply because the telescope has been fixed in place. Earth is still rotating, making the stars and the remnant appear to drift across the field of view. Without a tracking mechanism, a star would stretch into a streak, and the already delicate gas filaments would blur during the exposure. The telescope mount has to move slowly in a direction that compensates for Earth's rotation, keeping the same region of sky nearly fixed on the pixels for many minutes at a time. That motion is very small and almost impossible to notice when standing beside the instrument, but its precision determines the final shape of the image. A slight error repeated over a long period can turn a round star into an elongated one, soften the edge of a gas filament, and cause fine details to blend together. In an image of a bright target, such an error may sometimes be only a minor flaw. With a faint structure like the Cygnus Loop, every bit of added blur makes the signal harder to separate from the background. The atmosphere is also constantly moving while the sensor collects light. Layers of air at different temperatures bend incoming light again and again, creating the twinkling of stars seen by the eye. During a long exposure, countless tiny fluctuations are blended into the same image, making details softer. A very thin cloud can pass through without the observer noticing immediately, yet still change the brightness of the frame. A light breeze, humidity, and the expansion or contraction of the equipment with temperature can also leave small variations in the data. One very long exposure may seem like the most direct way to collect more light, but it also makes the entire dataset depend on a single stretch of time. If a satellite crosses the frame, a gust of wind shakes the telescope, or the tracking system drifts near the end of the exposure, the entire frame may lose its value. In practice, observing often takes a more cautious approach, dividing the total time into many shorter exposures, each preserving part of the light, and then combining them afterward. In each individual frame, the star field usually appears more clearly than the gas. The Cygnus Loop may show up only as extremely faint regions, sometimes difficult to recognize without already knowing where to look. But when many images are placed side by side, the real structure of the sky reveals an important property. It repeats. The stars remain in the same relative positions, the arc of gas keeps the same curve, and the faint glowing regions continue to appear exactly where they appeared in earlier frames. Random noise does not have that same stability. A bright point caused by electrical fluctuation may appear in one frame and vanish in the next. A slightly bright patch caused by a temporary change in the sensor does not repeat precisely in the shape of the remnant. When the images are aligned according to the positions of the stars and stacked together, the real signal continues to accumulate in the same place, while the irregularly changing noise is relatively smoothed out. You might compare this process to listening to a very quiet voice through many recordings. In each individual recording, background noise hides part of the sentence. When the recordings are aligned precisely and layered together, the syllables that always appear at the right moment become clearer, while random sounds that do not repeat gradually lose importance. Astronomical imaging also depends on repetition, except that what remains stable is the position of light on the sky. Adding more frames does not make image quality improve along a simple straight line. Bright regions appear relatively quickly, while increasingly faint structures require far more total collecting time. Each additional hour still has value, but to make a weak signal rise well above the noise, it may take many nights of observation. This is why a deep image of the Cygnus Loop may contain light gathered across several different nights, later combined as though it had all arrived in a single moment. The sensor also creates signals of its own. Heat within the material can generate electrical charge, even when no photons from the sky enter. Some pixels are more sensitive than others, a few always appear unusually bright, and the surface of the sensor never responds with perfect uniformity. Dust within the optical system can create soft, dark patches, while light reflecting inside the telescope may leave bands or halos that do not belong to the object being observed. Those distortions become especially important when the target is already only slightly brighter than the background. A bright patch may be mistaken for glowing gas if we do not know that it is a property of the sensor. A dark region may look like a cloud of interstellar dust, even though the cause is only a speck of dust near the camera. To preserve the real light from the remnant, the observer also has to measure the traces created by the instrument itself. Calibration frames are taken for that purpose. Some images are recorded when the sensor receives no external light, in order to measure thermal signal and abnormal pixels. Other frames use an evenly illuminated source to determine how the entire optical system distributes light across the surface of the sensor. When these patterns of error are reduced in the sky data, What remains more accurately reflects the amount of light that truly entered the telescope. Calibration does not make gas arcs appear where none exist. It is closer to cleaning a glass window before looking through it. Dust marks and reflected patches on the surface can hide or distort the scene beyond. Removing their influence simply helps the view appear closer to its real state. In astronomical imaging, that care is especially necessary because the structure being searched for is too faint to be separated by intuition alone. After calibration, alignment, and stacking, the image may still look quite pale compared with the pictures often seen in books or on screens. Much of the signal lies within a very narrow range of brightness, where a display and the human eye have difficulty distinguishing small differences. Processing expands those subtle contrasts, helping slightly brighter regions become easier to recognize without adding any structure beyond the data. Contrast adjustment is sometimes misunderstood as a way of making an image less truthful, but every form of data has to be presented in a way human senses can receive. Numbers are turned into graphs, radio waves are converted into images, and wavelengths the eye cannot see are assigned colors to reveal structure. In deep images of the Cygnus Loop, very small differences between regions are expanded, so the gas filaments become clearer, while their origin still lies in photons that truly reach the sensor. When the data are deep enough, the image begins to show more than the most prominent bright arcs. Faint connecting regions slowly emerge. An area that once seemed empty may reveal broad folds of gas, and a single band can open into many smaller lines lying close together. The complete loop still does not become a smooth, even circle, because the real structure is bent, broken, and shaped by the changing density of the interstellar medium. What changes is that the connection between parts that once seemed separate becomes easier to recognize. In the final image, many hours of observation are compressed into a single frame. Photons collected on the first night may stand beside photons that arrived on another night, even though several days may have passed on Earth between the two recordings. Compared with a journey lasting thousands of light years, that separation in time is almost negligible. When the data are combined, they all contribute to one unified image of the expanding shell. A camera does not see the Cygnus Loop faster than the human eye. It gives the light more time to leave a trace. The telescope widens the collecting area. The sensor preserves each small contribution, and stacking joins many intervals of time into a deeper measurement. A band of gas does not need to be bright enough in each individual second, as long as it keeps sending a steady signal and remains in the same position across observations. That ability to accumulate light carries us beyond the limits of immediate vision, but it does not yet separate the different kinds of light blending together. The sensor still receives photons from the remnant, from stars, from the sky background, and from many other sources in the same field of view. Light emitted by hydrogen and oxygen may fall onto the same pixel, while unrelated sources continue adding signal to the frame. To understand where the gas bands come from and why they appear in different colors, waiting longer is not enough. The light also has to be divided by wavelength, so each element can reveal its own signature. Once time has helped faint photons accumulate into a visible form, filters take on the next step, narrowing the stream of incoming light and clarifying each layer of matter glowing together within the vast loop. After many hours of exposure, the sensor can preserve enough photons for the faint gas arcs to gradually rise out of the sky background. Yet the light entering the telescope has never belonged only to the Cygnus Loop. Within the same field of view, there is light from stars, the thin glow of the atmosphere, light pollution from the ground, and countless other faint sources lying along the line of sight. All of it falls onto the sensor, overlapping in each pixel. So a deep image may contain a great deal of signal while still not clearly revealing which part comes from the gas layer we are trying to find. White light in everyday life often appears uniform, but inside it are many different wavelengths. When it passes through a prism, those wavelengths separate into a continuous band of color, from red through yellow and green to blue and violet. An astronomical filter does not necessarily create an entire spectrum the way a prism does. It works more like a very narrow doorway, allowing only a specific range of wavelengths to pass through while blocking most of the remaining light. For a diffuse object like the Cygnus Loop, that choice can make a greater difference than simply extending the exposure time. If the sensor collects all light at once, the weak signal from the remnant has to compete with every other source in the frame. When the filter preserves only a band of wavelengths where the gas layer emits strongly, many components of the sky background are reduced, while the signal we want to find continues to pass through. The gas arcs do not emit more photons, but the contrast between them and their surroundings becomes clearer. The foundation of this method lies in the structure of atoms. Gas in the remnant does not glow like a hot surface with a continuous color. The shock wave compresses, heats, and ionizes the material, causing electrons to be stripped from atoms or pushed into higher energy states. When an electron returns to a lower state, the atom releases a photon with a very specific amount of energy. Each energy level corresponds to a particular wavelength, much like a musical instrument with its own set of notes it can produce. Hydrogen, oxygen, and sulfur do not produce the same collection of wavelengths. A region of gas rich in hydrogen may emit strongly in the red line commonly called H-alpha, while doubly ionized oxygen produces prominent lines in the green-blue region of the spectrum. Ionized sulfur also leaves its own signatures toward the red. These wavelengths are not colors added after the image is complete. They were already present in the light leaving the remnant. It is just that the human eye and an ordinary color image have difficulty separating them from everything else. A narrowband filter is made to allow only a very small range around one of these emission lines to pass through. Most continuous light from stars and many background sources is strongly reduced, while photons within the target wavelength range still reach the sensor. With enough exposure time through an oxygen filter, the places where ionized oxygen is glowing will gradually appear. Switch to a hydrogen filter, and a different structure within the shell may become prominent, even though both observations are aimed at the same region of sky. What is fascinating is that those two images do not differ only in brightness. They may reveal shapes that are slightly offset from one another, gas bands with different widths, or layers of emission lying close side by side. This difference reflects the physical state of the gas after the shock wave has passed. Immediately behind the wavefront, the temperature and level of ionization may be very high. A little farther back, the material begins to cool. Electrons gradually recombine, and the elements glow in different ways. A blue band lying in front of a red band can sometimes be the trace of an entire sequence of changes taking place within the same layer of gas. In a wide-field image, these regions may appear as blue outlines running beside red or orange filaments, giving the impression that the colors were added to make the scene more dramatic. In reality, their arrangement can carry information about the speed of the shock wave, the density of the gas, and the amount of time that has passed since the material was affected. Color becomes a visual way to see physical states that could not be distinguished in a black and white image alone. Even so, it is important to separate two ideas that are often combined when people talk about astronomical color. The wavelengths recorded by the sensor are real data, but the colors displayed on a screen can be chosen in different ways. If a wavelength lies within the range visible to the human eye, the image processor may assign it a color close to the natural visual impression. In other cases, channels are assigned colors to increase the distinction between types of gas, helping structures avoid blending into one another. A red emission line may still be shown as red, while two lines that lie very close together may sometimes be separated into more distinct colors, so the viewer can recognize each layer more easily. In that case, the image is not trying to recreate exactly what a person would see if they stood near the remnant. It is more like a map, where colors are used to encode information. A topographic map may color high plateaus brown and lowlands green, even though the actual ground does not carry those exact colors across the entire region. What matters is the relationship between color and data, not whether every shade matches the direct experience of the eye. Narrowband images of the Cygnus Loop often stand out because of the contrast between blue, red, and orange. Blue may represent oxygen emission, while red or orange brings out hydrogen and sulfur, depending on the color palette being used. When the channels are combined, the gas filaments do not simply become brighter. They separate into multiple layers, allowing the viewer to recognize a region that is strong in oxygen but weak in hydrogen, or the reverse. Each color becomes a sign that the physical conditions in that place differ from the region beside it. Filters are also useful against light pollution, but their ability is not absolute. City lights emit many wavelengths, and some types of artificial light can fall close to the region the filter is meant to preserve. Moonlight, the atmosphere, and starlight still contribute to the data. A filter cannot turn the sky into a perfectly black background. It only reduces enough of the unwanted light to give the emission signal a better chance to stand out. The narrower the doorway, the less total light passes through. The sensor then needs a longer exposure to collect enough photons from the target wavelength. A narrowband filter can make the initial frame look much darker than an unfiltered image, but the remaining signal is far more selective. Instead of recording every sound in the room, the system listens for one very narrow note and spends a long time capturing it. There is a subtle trade-off in that choice. A very narrow filter separates an emission line more effectively, but it requires long exposure time and a stable observing system. A wider filter receives more light, but more of the background also passes through. Sky conditions, sensor sensitivity, the speed of the optical system, and the scientific goal all influence the final choice. There is no single filter that reveals the entire truth of the remnant. Each one opens a different part of the same picture. When the separate images are placed side by side, the changing nature of the Cygnus Loop becomes easier to notice. In the oxygen channel, some arcs may look sharp and thin, like an outline marking a fast-moving wavefront. In the hydrogen channel, the glowing region is sometimes broader, with many small folds appearing behind it. Sulfur may be weaker, but it adds information about regions of gas that have cooled and reorganized. These differences help researchers not only determine where the remnant is, but also understand how the material is changing as the shock wave passes through. Spectroscopy can go deeper by separating the light into many wavelengths and measuring the strength of each line. From this, astronomers can infer the temperature, density, chemical composition, and velocity of the gas. But for the goal of reconstructing the entire loop, filtered images offer a different advantage. They preserve spatial information across a wide area of sky. Each pixel records both the position of the gas band and which wavelength is glowing strongly there. A separate oxygen image may look like a drawing of thin wave edges. A hydrogen image may reveal softer regions surrounding them. When those two layers are combined with data from sulfur or broadband light, the three-dimensional structure of the shell does not appear completely, but the relationship between its parts becomes far richer in information. We are no longer just seeing where light exists. We begin to see different processes unfolding within the same band. Color in astronomical images is therefore both beautiful and functional. Its beauty does not stand apart from the science. It arises from the way atoms respond to the energy of the shock wave. Each blue or red line can be understood as the trace of electrons changing state, releasing photons, and sending them across thousands of light years. When the sensor waits long enough and the filter isolates the right wavelength, microscopic processes inside atoms become curves, stretching for light years across the sky. This also explains why the human eye does not see those colors directly. In darkness, rod cells dominate and provide an almost colorless impression. The number of photons in each emission line is too small to strongly stimulate the color-sensitive system, while a sensor can spend many hours on each channel and then combine them into a single image. The photograph does not show a scene the eye missed in one instant. It shows information accumulated and sorted in a way natural vision cannot perform. Each filter reveals only one part, and each part may require many exposures. A full-color image of the Cygnus Loop may be the result of hours of oxygen data, additional hours of hydrogen, sulfur, and sometimes broadband light to preserve a more natural star field. The channels are calibrated, aligned, and then combined, so the colors fall precisely on the structures that emitted them. When looking at the final image, it is easy to forget that the color layers were collected at different times. Blue photons may have reached the sensor on one night, red photons may have been recorded the next, and then all of them meet within the same frame during processing. They left the remnant long ago, but on Earth, humans continue to divide and arrange that journey by wavelength, so each element can leave behind its own signature. Thanks to filters, the glowing loop is no longer just a faint layer trying to rise out of the sky background. It becomes a structure with many voices, where oxygen highlights the shock fronts, hydrogen spreads through other regions of gas, and sulfur adds weaker layers. Exposure time allows those voices to become strong enough to record, while the filters keep them from blending completely into one another. Even after the bands have become clear and the colors have begun to reveal the physical structure, the full Cygnus Loop still presents another obstacle. Its nearly 3-degree width is larger than the field of view of many telescope systems used to record fine detail. A single frame may show a beautiful arc of gas, but it contains only a small part of the remnant, while the remaining regions lie beyond the edge of the sensor. To see the loop as wide as 6 full moons as one unified structure, the light must not only be accumulated and separated by wavelength. Many pieces of sky have to be photographed separately, kept at the same depth, and placed precisely back into their proper positions. Only when these separate tiles of sky meet does the full scale of the remnant emerge in a single image. After the light has been accumulated long enough and separated into individual wavelength bands, each frame begins to contain a clearer portion of the Cygnus Loop. An arc of gas in the east appears with thin blue folds, another region shows softer red bands, and farther along the shell, bright lines weave together like the traces of a surface wrinkled by a shock wave. Each individual image may be rich in detail, but even the most beautiful single frame often contains only part of a structure that spans nearly 3 degrees across the sky. That limit does not come from the rest of the remnant being too faint to record, but from the size of the field of view. A telescope designed to reveal fine detail usually covers only a narrow region. The sensor behind the telescope also has a finite size, so the portion of sky preserved in each exposure is like a small window. The Cygnus Loop is roughly 6 full moons across, while many optical systems used to capture its delicate gas folds can contain only a small part of that expanse. To see the entire remnant in a single image, the observer has to divide the sky into many neighboring tiles. Each tile is exposed long enough for the faint gas arcs to appear, and then the process is repeated with the adjacent region, continuing step by step until the full extent of the shell has been covered. The final image does not begin as one wide frame. It is gradually built from many pieces with overlapping edges, much like a large map assembled from a series of smaller map sheets. The overlap at the edge of each frame plays an important role. If 2 tiles only touch exactly at their borders, even a small error in position or optical distortion could create a gap between them. When each frame shares part of its star field with the next, the same stars become reference points that allow the 2 pieces to be aligned precisely. The system can recognize the same stellar pattern in both images, then rotate, shift, or make small adjustments until they match. The sky in each frame may seem like a flat surface, but optical systems often introduce very small distortions near the edges of an image. The spacing between stars may change slightly compared with the center. A straight line on the sky may become very subtly curved on the sensor, and the scale across the frame may not be perfectly uniform. These errors are difficult to notice in a single image, but they become more obvious when many pieces are placed beside one another. The mosaicing process has to correct them so the star field continues naturally, without a gas arc being displaced or a star appearing twice along a seam. The observing time is also rarely identical from one tile to another. One region may be captured on a moonless night, while the neighboring piece is recorded when the humidity is higher, or the sky background has become slightly brighter. Atmospheric transparency changes, the sensor temperature does not remain perfectly constant, and the background light may be stronger in one direction closer to the horizon, if the frames are combined directly, without balancing them. The borders between tiles will appear as bands of brightness and darkness, making the image look more like many pieces of fabric stitched together than one unified region of sky. To avoid this, the background brightness of each piece is measured and adjusted so the overlapping regions carry matching signal levels. Color also has to be balanced, especially when the data are collected through multiple filters or across different nights. An oxygen region exposed for longer should not become bluer simply because it received more imaging time than the neighboring area. Each channel has to be processed according to a consistent standard, so the remaining differences reflect the object rather than the observing schedule. This work requires precision, but it does not have to break the slow rhythm of the story. We might imagine the observer moving across a wide region of sky, placing each piece on a table and gently turning it until familiar stars find their proper positions again. A bright arc that ends at the edge of one image continues into the next. A gas band that seemed to disappear appears again in another tile with a similar curve, and when the two frames are aligned, the line of light connects across a boundary that existed only because of the way the data were collected. Each connection like this makes the larger structure clearer. The eastern part of the Cygnus Loop may contain thin, bright bands, while the western side appears as a more complex network. Between them, many fainter and less prominent regions link the major arcs into a single shared shell. If viewed one frame at a time, each region might seem like an independent nebula. Once the full mosaic is complete, the relationship between them becomes difficult to ignore. The idea of a mosaic is not unfamiliar in everyday life. A phone can sweep across a landscape and combine many frames into a panorama. In astronomy, the basic principle is similar, but the requirements are far stricter because the target is extremely faint and each piece may contain hours of observation. Small errors in brightness, color, or position can break the continuity of the gas filaments. A wide-field image becomes convincing only when the viewer no longer senses the borders between the original tiles. Some wide-field telescope systems can hold nearly the entire Cygnus Loop in a single frame, but that approach also carries a trade-off. The wider the field of view, the fewer pixels each detail occupies unless the sensor grows accordingly. The delicate folds of gas may appear less sharply defined than in an image recorded with a narrower optical system. A full-loop image gives a sense of scale, while a close-up image opens the structure inside each arc. The two approaches complement each other, much like needing both a map of an entire region and enlarged pages to read each road clearly. When the goal is to reconstruct the entire shell in high detail, a mosaic becomes the natural choice. Each tile can be captured with the same equipment, the same exposure depth, and the same filters, then joined into a field of view far wider than a single frame could provide. By then, the total data are not just a few photographs. They may include hundreds or thousands of exposures organized by position, wavelength, and quality before being merged into one. The stars help preserve a shared coordinate system, but the gas filaments themselves reveal whether the mosaic is truly seamless. A bright line should not suddenly change width as it crosses the boundary between two frames. Its color should also continue naturally, unless the data show that the physical state of the gas really changes there. Careful processing is meant to protect those small physical transitions, while removing changes caused only by the equipment or observing conditions. At a certain stage, the wide-field image may contain enough data, but still not feel like the final version. The dense star field can overwhelm the gas bands. The sky background between tiles may still differ slightly, and the faint emission regions may sit just at the edge of visibility. Contrast adjustment is applied across the entire image, not to make every area equally bright, but to preserve both the strong arcs and the extremely faint connecting regions, without stripping the stars of all their structure. A prominent bright region may tolerate a gentler display, while a weak gas layer needs stronger contrast before it appears. If the data are pushed too hard, the sky background becomes noisy, the gas bands lose their softness, and the colors can begin to feel artificial. If the processing is too restrained, many parts of the loop continue to disappear. The balance lies in making the structure clear enough for the viewer to recognize the connection between the pieces, while still preserving the sense that this is diffuse gas glowing in space, not an outline painted onto a black background. When the wavelength channels are combined, the problem gains another layer of complexity. Oxygen, hydrogen, and sulfur data may not have been collected on the same night or with the same total exposure time. Each channel has to be aligned to the star field, balanced by signal, and only then assigned color. A blue fold of gas has to fall precisely on the oxygen region that was recorded. A red band has to follow the corresponding hydrogen or sulfur data, and intermediate colors should appear only where the emission layers truly overlap. The final image becomes a kind of map that is both wide and deep. Horizontally, it joins many tiles of sky into the full remnant. Informationally, it combines multiple wavelengths to distinguish different states of gas. Temporally, it compresses hours, or even many nights, of observation into a single frame. These three layers meet in an image that can be seen in only a few seconds, even though the process that produced it passed through many stages and began with photons arriving one by one. This is where the comparison to 6 full moons receives its full payoff. Earlier, that number only helped convey the apparent width. In the mosaic, the viewer can see the entire region that 6 imagined lunar disks would occupy, while also recognizing that most of that area is not filled with uniform light. The gas arcs lie around the edges, thin bands stretch across many regions, and the middle remains relatively dark. Scale and faintness appear together in one frame, making the original paradox more intuitive than any single explanation could. A full loop image also shows that different names can belong to the same larger structure. Some parts of the Veil Nebula were once observed and named separately because they are separated on the sky and have distinct shapes. Seen one region at a time, they resemble independent clouds. Placed together in the same mosaic, those arcs become segments of one broad shell, each part glowing in its own way because its density, geometry, and gas state are not the same. That unity does not erase the differences between regions. On the contrary, the wide image gives those differences more context. A sharp, thin band on one side can be compared with a more tangled region on the opposite side. Places where the shell moves through a thinner medium appear different from regions interacting with dense clouds of gas. The full view helps the viewer understand that this is not a smooth ring with a few damaged spots, but a remnant carrying the imprint of the environment it has crossed. If we stop at a close-up, the beauty lies in the folds of gas. When we step back far enough to see the entire loop, the beauty shifts into a sense of scale. A band that once seemed to fill the whole frame becomes only a small segment of a shell nearly 3 degrees wide. The delicate details do not disappear. They are placed inside a larger structure, like the vein of a leaf gradually becoming part of an entire canopy as the view opens outward. The mosaic also reminds us that seeing the whole thing does not mean every part has been observed with the same certainty. Some regions remain extremely faint, some may stand out more strongly at wavelengths beyond visible light, and the exact boundary of the shell is not always sharp. The full view is the best reconstruction from the available data, not an absolute outline that nature has drawn in advance. Even so, that reconstruction is enough to connect the pieces into a unified story. The telescope widens the entrance for light, the sensor preserves photons over time, The filters separate each layer of emission, and the mosaic returns the separate regions to their proper places on the sky. Each step solves a different limitation, and only when all of them are combined does the Cygnus Loop appear closer to the whole that the unaided eye cannot perceive. One detail makes the image feel even more alive. If frames of the same region are taken many years apart, the gas filaments do not remain perfectly fixed against the background stars. Their extremely small motion can be measured, showing that the shell is still expanding through the interstellar medium. A structure that looks motionless in a single image turns out to be moving, only at a rhythm far too slow for one observation to reveal. The wide-field image does not merely bring the loop back from darkness. It also preserves one moment in the process of the loop continuing to grow. The bright arcs we assemble today will not remain forever in exactly the same places. Across years, centuries, and far longer spans of time, the wavefront continues to move outward, encountering new gas and changing shape in ways that are very slow by the measure of a human life. From a region of sky that seemed almost empty, humans have gathered individual photons, divided the light by wavelength, preserved it across many nights, and placed each piece back where it belongs. The result is not a loop created during processing, but a structure that was already spread out there in space, finally given enough time and enough room to appear within a single frame. And when 6 imagined moons can be laid across that image, the original question changes in tone. We are no longer only asking why an object so large is so hard to see. What becomes more remarkable is how a quantity of light so faint, after traveling for thousands of years, is still enough for humans to reconstruct the shape of a giant shell and recognize that it has never truly stood still. Once the wide-field image of the Cygnus Loop has been assembled, the enormous structure can easily take on the quiet appearance of an object completed long ago. The arcs of gas seem fixed among the star field. The blue and red lines hold their shape within the frame, and the dark region in the center gives the impression of the hollow part of an ancient ring hanging motionless in the sky. Its distance of thousands of light years makes its motion feel even more remote, because what humans see seems to belong to a past that had already closed before our own history began. In reality, the image preserves only a very thin slice of a process that is still continuing. The shell is not standing still around the place where the star once existed. The shock wave is still moving outward, entering new regions of gas and changing shape as it encounters environments of different density. The scale of the remnant makes that motion difficult to notice in a single night, a single year, or even across much of a human lifetime. But when 2 sufficiently sharp images are taken nearly 2 decades apart, the gas filaments begin to reveal that they have moved away from their earlier positions. A small region along the edge of the Cygnus Loop was observed by the Hubble Space Telescope in 2001 and then revisited in 2020. 19 years is a long span in human life, long enough for a child to grow into an adult and for a city to change many of its familiar outlines. For a structure roughly 120 light-years across, that interval is almost only an instant. Even so, Hubble's resolution is high enough to detect that the wave front has shifted by a small amount relative to the stars behind it. When the 2 images are aligned to the star field and then alternated on the screen, the distant points of light remain almost fixed, while the foreground gas filaments slide slightly outward. The shift is not large enough for the viewer to immediately see the loop expanding like a bubble being inflated. It appears more subtly. A bright edge leaves its former position. A thin band moves a little farther into the darker region ahead, and the distance between the wave front and the reference stars changes just enough to be measured. It is the stability of the background stars that makes this motion visible. Most of the stars in the image are so distant that their own motions over 19 years are very small compared with the scale of the frame, or they can be accounted for during analysis. They form a natural coordinate system, allowing astronomers to place the 2 observations on top of each other with high precision. Once the star field matches, the part that remains offset belongs to the gas layer, moving outward. The measurement on the sky first gives only an angular shift, extremely small compared with the size of the full loop. To convert that into a real velocity, researchers have to combine the shift with the time between the two images and the distance from Earth to the remnant. The farther away the object is, the larger the physical distance represented by a given angular motion. Uncertainties in the distance also affect the velocity that is inferred, so published values are always tied to the precision of the related measurements. According to current estimates, the wavefront in the region observed by Hubble is still moving at more than 800,000 kilometers per hour. That number is enormous by any familiar measure on Earth, but when set against the more than 100 light-year diameter of the remnant, it does not create an obvious change over a short span of time. An object can be moving extremely fast and still appear almost motionless if it is distant enough and large enough. This is also why the sky often seems still, even though almost everything in it is in motion. Earth orbits the sun moves through the Milky Way, stars follow their own paths, and clouds of gas continually change under the influence of gravity, radiation, and shock waves. Distance compresses these motions into very small changes within our view. Only when the observing time becomes long and positions are measured precisely enough does the sky stop being a fixed picture and become a changing landscape. At the edge of the Cygnus Loop, the thing that moves should not be understood simply as a ribbon of material flying intact through space. The wavefront is the boundary where the energy of the explosion continues to pass into the interstellar medium. The gas ahead of it may be cold, thin, and almost invisible in visible light. When the shock wave passes through, that material is compressed and heated, its atoms are excited or ionized, and it begins to emit light. The observed bright band marks where that transformation is happening, or has only recently happened. A ripple crossing the surface of a lake offers a familiar comparison, as long as the two phenomena are not treated as identical. The ripple line can move across the water while each parcel of water mainly oscillates around its own position, rather than racing from one shore to the other. In a supernova remnant, real material is also pushed and accelerated, but the wavefront is still a structure that carries energy through a medium. The bright band moving outward reflects both the motion of the gas and the fact that new regions are being affected by the shock wave. That makes a time sequence of images far richer than a simple position measurement. As the bright edge advances, it shows that the shock wave is still encountering new material. The shape of the gas band reveals whether the environment ahead is uniform or not, while its brightness and color help determine how the gas responds after being disturbed. One part of the shell may move quickly through a sparse region, while another slows as it meets denser gas, causing an already uneven boundary to keep changing over time. In the region observed by Hubble, light from hydrogen may appear as thin orange filaments, while cooling ionized oxygen appears in blue bands. These two color layers do not necessarily move and change in exactly the same way, because they represent different stages of the gas behind the wavefront. Neutral hydrogen ahead of the shock may be excited very quickly as the shock passes through, while oxygen glows in hot gas that has undergone ionization and continues to evolve. The small separation between these emission layers acts as a kind of physical clock. Gas passes through the wavefront first, is heated, and then its ionization state and temperature change over time. If researchers know the velocity of the gas flow and can measure the width between the glowing regions, they can estimate how quickly cooling and restructuring take place. A beautiful image, in that sense, is also a record of temperature, density, and the time that has passed since the material encountered the shock wave. The thin filaments also do not maintain the same brightness forever. As the gas continues to cool, electrons change states and density shifts, so an emission line may strengthen during one stage and then gradually weaken. A region glowing in hydrogen today will not necessarily have the same appearance over centuries. Oxygen, sulfur, and other wavelengths also respond according to their own thermal histories. The loop is not only expanding in size, but changing in the way it emits light, even though most of that change unfolds too slowly for a person to notice through direct observation. Looking back at two images taken 19 years apart, we do not see the entire Cygnus Loop shift all at once. Hubble observes one very small slice of the shell in great detail, where the gas lines can be measured precisely. From that small portion, combined with observations of other regions and spectroscopic measurements, astronomers build a broader picture of the remnant's expansion. This is like studying the motion of a wavefront through a few carefully observed segments, then placing them on a map of the whole region to understand the larger process. Wide-field images and close-up images play two different roles. The mosaic shows the nearly 6-moon scale of the remnant and the relationship between its major arcs. The high-resolution image narrows the view to a very small region, enough for individual gas filaments to have measurable width and for their motion over time to be detected. When these two levels meet, the remnant appears both as a giant shell and as a wave front whose edges can be followed almost line by line. The measured velocity also helps test estimates of the remnant's age and distance, though no simple calculation by itself gives a perfect answer. If the shell had always expanded at its current speed, one could divide its size by that velocity to estimate the time since the explosion. In reality, the shock wave has slowed as it has swept up interstellar material, and its speed is not the same in every direction. To trace the history backward, models have to account for the amount of material that has been gathered up, the density of the surrounding medium, and the remnant's current stage of evolution. What is more certain is that the explosion occurred tens of thousands of years ago, in the source's own time, and the shell has not yet fully dissolved into its surroundings. The original energy continues to be distributed through an ever-growing volume, heating gas, accelerating material, and producing radiation at many wavelengths. The boundary will keep expanding, but its speed and brightness will change as the wave enters regions with different conditions. In the very distant future, the remnant will not forever keep the recognizable shape of a loop. The shock wave will continue to lose energy, its velocity will gradually decrease, and the disturbed material will mix with the interstellar medium. The thin, bright lines will change, fade, and eventually no longer stand apart clearly as a separate structure. Gas that once belonged to the star, along with gas swept up by the explosion, will return to the material cycle of the Milky Way, possibly becoming part of new clouds and later generations of stars. Although that outcome lies far beyond the scale of human time, the sequence of images from 2001 and 2020 has allowed us to see a tiny part of the motion leading toward it. We do not need to wait centuries to recognize that the shell is changing. The precision of the instrument has reduced the required interval to less than 2 decades. A change that the unaided eye would treat as motionless becomes measurable motion through 2 observations, the same star field, and enough patience to place them side by side. The moment the images alternate on the screen creates a different feeling from a still photograph. The gas band is no longer only a trace of the past, but a boundary moving forward. The photons in the earlier image and the later image left the remnant at slightly different times, carrying 2 states of the same wave front. Humans are not only looking across distance, they are placing 2 slices of time beside each other to see the universe change itself. That discovery returns to enrich the question of visibility. The Cygnus Loop is too faint for the unaided eye to recognize, but when its light is accumulated, filtered, assembled, and compared across many years, it provides more than a shape. A signal so weak that it is invisible in a single night still contains information about the velocity, temperature, and evolution of the shell. Faintness does not mean a lack of data. Sometimes a very small amount of light, if measured carefully enough, can describe the motion of a structure more than 100 light-years across. 6 full moons on the sky, in this sense, are not a loop that has simply been lying still for humans to find. They are the present projection of a process that is still expanding, still touching new gas, and still leaving new lines of light behind the wave front. Each wide-field image preserves one moment of the structure, and each return in the future will find it in a slightly different state. From the window of a room, that region of sky still shows no motion. The stars remain scattered, and the darkness between them still seems to contain nothing especially remarkable. Only when the light is gathered across many years does that stillness reveal its true nature. A giant remnant moving too slowly within our view, yet still fast enough for Hubble to recognize that its edge has advanced between two observations. The nearly invisible loop is not only wider than the eye can guess, it is also more alive than the apparent stillness of the sky suggests. Through the time of the sensor, each band of gas shows that the universe has not finished making this image, because the shell is still expanding, and the light from new regions touched by the shock wave is only now beginning its journey toward us. After images taken nearly 2 decades apart showed that the edge of the Cygnus Loop is still moving outward, the loop no longer seems like a relic that belongs entirely to the past. Its thin gas filaments are still traveling through the interstellar medium, heating new material and changing so slowly that only a sufficiently precise instrument can detect the motion. And yet, even the deepest optical images, where the blue and red arcs appear clearly, record only part of what is happening within that same region of space. We can begin with a bright band near the edge of the shell, where visible light draws a thin curve among the stars. Through a filter sensitive to oxygen, that band may appear sharp and narrow, like the edge of a sheet of gas viewed almost side-on. Hydrogen data adds softer regions just behind it, showing gas that has been affected by the shock wave and is continuing to change state. If this were the only image we had, it would be easy to think that the most important part of the remnant lies within those delicate lines of light. When the same region is observed in X-rays, the scene no longer keeps the same shape. The optical outline still marks an important part of the wavefront, but behind it there may be a broader glowing region where gas has been heated to temperatures of millions of degrees. That material does not form a flame in the familiar earthly sense. Its density is still extremely low, but individual particles carry great energy after being affected by the shock wave, causing the whole volume of gas to emit radiation at energies higher than the light our eyes can see. The optical image shows us places where material produces clear emission lines in the visible range. X-rays extend our view into the hotter gas deeper behind the shock. The two images do not contradict each other, nor are they simply differently colored versions of the same scene. They record different states of matter coexisting within a small part of the remnant. If the optical outline is like a fold brought out by light, the X-ray region behind it is like the volume of space that the fold encloses. One side holds the thin gas filaments, where geometry and emission conditions create a clear edge. The other reveals a broader volume of hot plasma, a state in which electrons have been stripped from atoms and move among ions. The part visible to the eye is only the thinnest layer of a structure with far greater depth. Earth's atmosphere blocks most X-rays from space, so this data has to be collected by observatories operating above the atmosphere. The instrument does not see blue or red in the way humans perceive them. Instead, it measures the position and energy of X-ray photons. Those values are then converted into an image the eye can recognize, often by assigning colors to different energy ranges. Color in an X-ray image is a language for displaying data, while the hot gas behind it is a real part of the remnant. When optical and X-ray images are placed side by side, the boundary of the Cygnus Loop begins to lose its simple appearance. In some places, the optical filaments lie close to the edge of the X-ray emission, showing where the wavefront is encountering gas dense enough to create bright threads. Other regions may be strong in X-rays but weaker in optical light, often associated with thinner gas, where the shock wave is still moving quickly and maintaining a high temperature. It is the same shell, but the conditions along each segment are not the same, so each wavelength selects a different part of the process. Shift to radio waves, and that region of sky changes once again. Radio light does not mainly come from atoms moving between energy levels the way optical emission lines do. A major part of it is produced by high-energy electrons moving through magnetic fields. When the paths of charged particles are bent, they release synchrotron radiation, leaving a signal at wavelengths far longer than visible light. The shock wave in the remnant does more than heat the gas. It can also accelerate some particles to high energies, while compressing and distorting the magnetic field in the interstellar medium. Radio maps allow us to trace regions where high-energy electrons and magnetic fields are present together, opening a layer of physics that almost does not appear in optical images. A faint arc to the eye may lie within a broader radio region, while a place that stands out in optical light is not necessarily the strongest part at longer wavelengths. Place these three ways of observing over the same small region of the shell, and a sequence begins to emerge. The optical band points to layers of gas with the right conditions to produce visible emission lines. X-rays reveal the very hot volume of gas behind the shock wave. Radio records the traces of high-energy particles and magnetic fields that the wavefront has compressed or disturbed. These are not three different objects, but three expressions of the same interaction between the energy of the explosion and the surrounding medium. This changes the meaning of the phrase, seeing the loop. A wide-field optical image can reconstruct the gas arcs spanning 6 full moons across the sky, but it does not record all the material within that region. The visible portion is not a solid shell containing everything important on a single surface. Inside and around the bright lines are hot gas, magnetic fields, high-energy particles, and regions of matter that emit strongly beyond the reach of human sight. Ultraviolet light adds a transitional range between optical light and X-rays. Some atoms emit ultraviolet lines that are sensitive to the temperature and ionization level of the gas just behind the wavefront. This data can help trace how matter moves from a freshly heated state into layers that begin to cool and glow in optical light. Infrared light, on the other hand, is more sensitive to dust and cooler regions of gas, revealing dust grains as they absorb energy, heat up, or are altered within the environment of the remnant. These two windows add necessary details, but they do not change the main point. The same region of sky contains more states of matter than an image visible to the eye can express. Not every part of the Cygnus Loop shines at all wavelengths. A region of very hot, diffuse gas may stand out in X-rays without producing many optical filaments. Where the shock wave meets a denser cloud of gas, it slows down, compresses the material strongly, and makes the visible threads clearer, while the X-ray emission may change. If there is a great deal of dust, the infrared signal increases. If high-energy particles and magnetic fields are strong, radio adds another layer of structure. The mismatch between images is exactly what makes them valuable, because each difference reveals that the physical conditions have changed from one region to the next. When multi-wavelength maps are combined, color is often used to keep the layers from blending completely into one another. X-rays may be shown in blue, radio in another shade, while optical light preserves the red or green-blue bands of emission lines. This is not the scene a person would see if they could stand near the remnant. It is more like a map in which color carries meaning, showing which type of radiation each part of the image comes from. That form of display is still based on real data. X-ray photons have reached sensors above the atmosphere. Radio waves have produced signals in antennas, and optical light has passed through filters before falling onto pixels. Assigning color simply translates different measurements into a language the eye can compare within the same frame. Because of that, a region that seemed to contain only a thin gas filament may reveal a broader volume of hot space, while a faint segment of the loop may begin to show the activity of high-energy particles and magnetic fields. This difference also explains why the boundary of the remnant is not exactly the same at every wavelength. The same shell still covers a very large region of sky, but the extent of optical, X-ray, and radio emission does not necessarily end along the same line. The sensitivity and resolution of the instruments also affect which parts are recorded. Saying that the loop spans 6 full moons is a useful description of its general optical extent, but it does not mean every map at every wavelength creates an identical boundary. If we look only with the eye, that region of sky is almost empty. If we take a deep image in visible light, the gas filaments begin to appear. Open the X-ray window, and the hot gas behind the shock enters the picture. Radio adds high-energy particles and magnetic fields, while ultraviolet and infrared clarify transitional states and disturb dust. Each time the method of observation changes, the remnant does not become a new object. The limit of the measurement simply moves to a different place. This does not reduce the value of the experience of seeing with human eyes. A dark sky with scattered stars is still a real image, created by the exact range of light the retina can receive. Being incomplete does not mean being false. The eyes give humans a window wide enough to navigate, recognize color, and live within the nearby world, but they were not formed to measure X-rays from million-degree plasma or radio waves emitted by high-energy electrons thousands of light-years away. Telescopes expand that window in two directions. On one side, optical systems and sensors draw extremely faint visible signals out of the background through exposure time, filters, and mosaics. On the other, specialized observatories turn forms of radiation entirely outside human vision into data that can be seen. The same target in the sky is questioned through many kinds of light, and each answer adds to the part the previous one could not tell. Through this way of observing, the Cygnus Loop is no longer only a beautiful outline around a dark region. It becomes a shell containing many states of matter, visible gas filaments, cooling and emitting light, very hot plasma spread behind them, high-energy electrons moving through magnetic fields, and dust absorbing and re-emitting energy. All of it began with an ancient explosion, but it evolves along different paths as the shock wave continues to travel through the interstellar medium. Returning to the original region of sky, the absence of the loop before the human eye now carries a deeper meaning. We do not simply fail to see the optical filaments because their surface brightness is too low. We also fail to see most of the other processes because they emit signals outside the range the body can sense. The darkness between the stars has never been a completely empty backdrop. It contains many layers of radiation traveling toward Earth together, each carrying part of the remnant's history. The full loop image, then, is not the only portrait of the Cygnus Loop, but one of many possible translations made from light. Optical light gives us the thin filaments needed to recognize the broad shell. X-rays open the hotter gas behind them. Radio traces the energy of particles and magnetic fields. When these translations are placed beside one another, the loop does not simply become easier to see. It gradually gains depth, temperature, and motion. A region of sky can look empty simply because the eye is listening to the wrong kind of light. Change the method of observation, and the darkness begins to take on structure, open another wavelength, and material that was previously invisible leaves its own trace. The Cygnus Loop remains in the same position, still spread across the sky, still sending signals toward Earth, but the image humans receive always depends on which doorway of light has been opened. Outside the window, the moon can still fit behind the tip of a finger if we close one eye and raise a hand to the right position. The bright disk has not become smaller, but distance has allowed a world thousands of kilometers wide to temporarily disappear behind a very small gesture. When the hand drops, the moon returns almost immediately, clear and familiar against the sky. In another region of the sky, among the stars of Cygnus, a structure nearly as wide as 6 moons placed side by side still lies in darkness. It does not appear as a glowing ring hanging above the rooftops, nor does it reveal the soft blue and orange lines seen in astronomical images. To someone who happens to look up, that place is only a quiet patch of sky, with a few scattered stars and very little sign that a giant shell is out there. But that darkness now carries a different meaning. The Cygnus Loop has never been too small for the eye to see. On the contrary, it is so broad that its light is spread across a large region of sky, making each part of the structure only slightly brighter than the background around it. A distant star can easily catch the eye because its signal is concentrated almost into a point, while the light from the thin shell of gas is stretched along wide arcs, fading through the star field and blending into a background that has never been completely dark. Human eyes have done very well the work they were shaped to do. They recognize faces, motion, color, and changes in the nearby world around us. When night falls, vision can become more sensitive, but it still has to receive the sky moment by moment. Photons that arrive too sparsely, colors that are too weak, and outlines that change too subtly will not assemble themselves into a complete loop within perception. Humans only began to see that structure by learning how to extend the patience of the senses. A mirror wider than the pupil gathers more light. A sensor preserves photons that would otherwise pass through each instant. Many observations are placed together, allowing weak but stable traces to gradually separate from random noise. Light is selected by wavelength. Separate pieces of sky are returned to their correct positions, and after a great deal of waiting, the scattered arcs begin to recover their connection within a single image. That image does not make the universe brighter. It simply brings a signal too delicate into a range where humans can recognize it. When the entire remnant appears, the loop also reveals itself to be more complex than its name suggests. In space, it is an uneven three-dimensional shell, made of curving sheets of gas that are still expanding. The thin filaments in the image may be parts of the shell seen almost edge-on, where light, the geometry and brightness simply do not allow those parts to stand out clearly. Even the stillness of the structure is only a feeling created by distance. Across images taken many years apart, some gas filaments have shifted relative to the background stars. The shock wave is still moving outward, encountering new material and continuing to change the gas around it. The loop we see today is only one slice in time of a much longer process, unfolding too slowly for the eye to notice in a single night, but still clearly enough for patient measurements to record. Visible light also tells only part of the story. Behind the soft gas filaments are hotter regions of matter, high-energy particles, and layers of radiation beyond the reach of vision. The sky before our eyes is real, but it is only a small window opened within a much wider spectrum of light. Each new instrument does not replace the old image, but adds another layer, allowing the darkness to gradually gain temperature, motion, composition, and depth. Perhaps the most memorable thing is not that a structure as wide as 6 moons has remained hidden from the naked eye, but that humans have learned that seeing does not always happen instantly. Some things appear only when we wait longer, measure more precisely, and accept that our senses receive only a very small part of the world. Light from the Cygnus Loop continues to arrive at Earth, one photon at a time, whether or not a telescope is pointed toward it. The gas continues to change state, the wave front continues through the interstellar medium, and the faint signals still carry the trace of a star that vanished long ago. Their existence does not depend on whether humans have recognized them yet. When the hand lowers, the moon returns to the sky, while the distant loop remains beyond the limits of the eye. That invisibility no longer feels like an empty space, because behind the darkness is a shell more than 100 light-years wide, preserved in photons that traveled for thousands of years before reaching Earth. The sky did not become fuller after humans built telescopes. What changed was the way we learned to recognize what had already been present, even when it was too faint, too slow, or beyond the range of the senses. Night still spreads above the rooftops, and the region of sky large enough to hold 6 moons still appears as quiet as before. The loop does not emerge, but its light continues to reach Earth, so gentle that it does not change the color of the darkness, yet enough to remind us that the space before our eyes always contains more than humans can see.